graph. Now let V be a vertex of G such that degree of V equal to delta of G. So we choose a vertex V whose degree is the minimum degree of that graph G. So here we take a vertex V, and what's the degree of V? It is the minimum degree of that graph. The degree of V equal to delta of G. Then we remove delta G edges incident with V. Remove delta G edges incident with V. So we choose a vertex V, and V has delta G, say 1, 2, 3, etc. How many edges? Delta G edges are incident to V, and remove all these edges from this graph, from our graph G. So from our graph G, we chose a vertex V whose degree is the minimum degree of the graph. So we remove all these edges incident to this vertex V. What will be our resulting graph? In our resulting graph G dash, we have this vertex V as an isolated vertex. Okay, so the resulting graph G dash has V as an isolated vertex. Resulting graph G dash has V as an isolated vertex. Now, so therefore, since G dash has V as an isolated vertex, we have G dash is disconnected. Therefore G dash is disconnected, or G dash can either be a trivial graph. Trivial graph means G dash can either be at a single vertex. So G dash is disconnected or a trivial graph. So what we can say? By deleting all these delta edges incident to this vertex, delta G edges incident to this vertex V, we got a disconnected graph. So what will be the edge connectivity? Lambda of G will be less than or equal to delta of G. Okay, since lambda of G is the minimum number of edges to be deleted from the graph, so that the resulting graph is disconnected, we can clearly say that lambda of G is less than or equal to delta of G. So we get the one side of the inequality, lambda of G is less than or equal to delta of G. Now we need to prove that this left hand side inequality, we need to prove that kappa of G is less than or equal to lambda of G. So we are going to prove that, we are about to prove that kappa of G is less than or equal to lambda of G. Now see what happens when lambda of G is equal to 0. If lambda of G equal to 0, what does it mean? Lambda of G is equal to 0. It means that none of the edges has to be deleted in order to make the graph to be disconnected. The lambda of G equal to 0, that means already the graph is disconnected, or that graph is a trivial graph. Okay, so if lambda of G is equal to 0, that means that G is either disconnected or a trivial graph. G is either disconnected or a trivial graph. So since G is already disconnected, we can clearly say that the kappa of G is equal to 0. Okay, so this implies kappa of G is equal to 0. So when lambda of G is equal to 0, we get also what kappa of G equal to also 0. Now what about if lambda of G equal to 1? Lambda of G equal to 1 means a single edge is needed to be deleted in order to disconnect the graph. That means what? That graph G has a edge which is a bridge. So lambda of G is equal to 1 implies that G is a connected graph containing a bridge. Okay, so G is a connected graph containing a bridge. So if we delete that bridge, the graph will be disconnected, and hence lambda of G is equal to 1. So if we have lambda of G is equal to 1, we will come to the conclusion that G is a connected graph containing a bridge. Then that means what? G can either be a K2, G is simply an edge K2, or G is a connected graph, or G is a connected graph having at least one G is a connected graph having at least one cut vertex. Yes. Okay. So G contains a bridge. So we can have it either two conclusions. If G has a bridge, then either the graph G itself is a edge K2. If it is a K2, then what happened? If G is a K2, then clearly deleting a single vertex, the graph will be disconnected, and we can say that the vertex connectivity will be 1. Okay, if we delete this vertex, then the resulting graph will be a trivial graph. So what is the vertex connectivity? Vertex connectivity will be 1 in that case. Otherwise, what is the other option? If G is either a K2 or G is a connected graph having at least, so G is a connected graph containing this. Other cases, G can be a graph containing this bridge. Since this edge is a bridge, if we can delete here, some edges will be there like this, and here also some edges will be there. Okay, this edge will act as a bridge. So what happen if we delete this vertex? If we delete this vertex, this connection will get lost, and so this vertex is a cut vertex, and the resulting graph is disconnected. Or instead of this vertex, even if we delete this vertex also, the resulting graph will be disconnected, and hence what we can say, lambda of G is 1. So we come to conclusion that G is either a K2 or G is a connected graph having at least one cut vertex. So what we get, that this implies that deleting that cut vertex, we get a disconnected graph. This implies kappa of G equal to 1. So what we come to the conclusion, we start with lambda G is equal to 1, and we got that kappa of G is equal to 1. So for lambda G is equal to 0, we got kappa G is equal to 0, and if lambda G is equal to 1, we get kappa G is equal to 1. What we need to prove? We need to prove that kappa G less than or equal to lambda of G. So we have seen that for 0 and 1, we got kappa of lambda of G equal to lambda of G for 0 and 1. Now what happens when lambda G greater than or equal to 2? Now assume lambda g greater than or equal to 2. Assume that lambda g greater than or equal to 2. Let u be an edge cut set sorry for the inconvenience. Okay, continue. Let u be an edge cut set of G. U be an edge cut set of G having cardinality lambda of G. Let u be an edge cut set of G having cardinality lambda of G, and let E is equal to UV be an edge of U. So we assume that lambda g greater than or equal to 2 and u be an edge cut set having the cardinality lambda of g, and let E be a one edge among U. Now if the edges of delete the edges, now delete from G the edges U minus E. Now what we are doing, we delete all those edges from U except the edge E from G. What will happen? What we can say about the resulting graph H1? What will be the resulting graph H1? We had taken U is the edge cut set of the having cardinality lambda of G. That means what? Since U has the cardinality lambda of G and lambda of G is the minimum number of edges to be deleted in order to disconnect the graph. Okay. So here we had done that we have delete all those edges from G, all those edges from U except this edge E. We keep one edge E and delete all other edges from U. So the resulting graph H1 will still be, H1 is connected or disconnected? What you can say? H1 will be connected. Why it is connected? Since we have not deleted that edge E, this edge E is still in our graph H1. When will that graph will disconnect? If we delete all the edges from U only, that the resulting graph will be disconnected. But we have deleted all the edges except this edge E. So the resulting graph H1 will be still be connected, and that graph H1 has, in that graph H1, what will be that edge E? That E will act as a bridge. Okay. So in that graph H1 is connected and contains E as a bridge. Okay. So this graph H1 is connected, the resulting graph H1 is connected, and it contains E as a bridge. Now, for each edge in For each edge in U minus E, select an incident vertex. For each edge in U minus E, select an incident vertex different from U and V. What you have done here? Here from that graph, I can show it here.